So the last thing that we talked, oh, you guys can't see this. The last thing that we talked about on Wednesday before we wrap things up was the Bodie plot for whenever we had a pole at the origin, right? So just to recap things incredibly quickly, so for a system whose transfer function h of s was simply 1 over s, what we saw was that our frequency response looked something like this. So here is h of s measured in decibels on this particular axis. And then here is s on this axis. Let's put 10 to the 0 right here. So this would be 10 to the minus 1, 10 to the minus 2, 10 to the plus 1, 10 to the plus 2. And it our frequency response crossed our horizontal axis at s is equal to 1, or right here, and it had a slope of negative 20 decibels per decade. So that's what we saw. Then we worked a couple of little examples. Now let's move along and see what happens if we have a 0 at the origin. So a 0 at the origin means that our system would have a transfer function of just s in the numerator. So I'm going to do something a little weird here, and I'm going to let this s just in the numerator be the same thing as 1 divided by 1 over s. Okay? The reason why I'm choosing to represent s in the numerator like so is because I know what the frequency response of the number 1 is going to look like. It's a constant line at 0 decibels because 20 log of 1 is 0. And I also know what the frequency response of 1 over s is. It's literally up here, right? So when I'm doing the logarithms, effectively I would just have 20 log of 1 minus 20 log of 1 over s. Adding those two things together should tell me what's happening whenever I have a 0 at the origin, right? So this is just going to be 20 log of 1 minus 20 log of 1 over s. So graphically, that would look something like this. So here's 20 log of, actually, let me just do it as h of s and dB. That's less writing to do. And here's s. Once again, here's 10 to the 0, 10 to the minus 1, 10 to the minus 2, 10 to the positive 1, 10 to the positive 2, and so on and so forth, right? So if I do just this part in red, we would have this line right here. If I did this part in blue, remember that I'm doing minus 20 log of this. So earlier, when we had positive 20 log of 1 over s, it looks something like this with a slope of negative 20 decibels per decade. So when I do minus that, it should be the opposite direction. So I'll have a slope of positive 20 decibels per decade. Like so. And when I add these two together, point by point, I'm just going to get this line right here because I'm adding 0 dBs because of that constant contribution, right? So all I get is just a line that crosses the horizontal axis at s is equal to 1, which is the same thing as 10 to the 0th power, having a slope of 20 decibels per decade. If I had a transfer function of s squared, how would this graph change? It'd be steeper. So it'd be increasing at a slope of 40 decibels per decade, because I would just add another one of these and adding it point by point. So at this point right here, which will be corresponding to roughly negative 30 dB, I would have another one of them. So it'd be down at negative 60 dB. It'd still cross at this exact same point, and it would be up here at positive 60 decibels or whatever. This point over here. But yeah, pretty straightforward stuff. Okay. So I feel like we're pretty comfortable with having a pole at the origin, and a 0 at the origin should make intuitive sense because it's literally just the exact same graph, except that we've flipped it around. Okay. So now let's see what happens when we start putting in poles and zeros that aren't at the origin. Okay. So let's call this a simple pole. So let's say that my system has a transfer function of, instead of 1 over s, we'll do 1 over s plus 1. So let's make some predictions here, okay? So for s is much less than 1, right? So actually, let's start here really quickly. I should be able to say by inspection that I have a pole at s is equal to -1 here, just by looking at this thing, right? That's what's going to make my denominator go to 0 and make this thing blow up. So when our system's frequency is much less than 1, what does this thing look like? So h of s should be approximately equal to 1 over 1, which is just 1. Absolutely right. So at very low frequencies, our frequency response is going to be that of a constant value of 1. So it's just going to look like 0 dBs. So let's put that down. Okay. So here we have h of s measured in decibels. Here's s, 10 to the 0, 10 to the -1, 10 to the -2, 10 to the +1, 10 to the +2. So I'm going to start with just a flat line like so, representing what's going on here. And I know that realistically, this should actually only be true up until somewhere close to s is equal to 1, right? Because here we're under the assumption that we're only considering cases where s is much less than 1. Now let's talk about what happens for s much greater than 1. So when s is much greater than 1, then I will have 1 over S plus something small in comparison to S. So it's going to look approximately like 1 over S. So when I have 1 over S, remember that that is going to look something like this. And so what I'm going to do is I'm simply going to put these two parts together. So in a hand plot, I'll do the hand plot in red. We would have a line like so, and then a line like so, right? So we have a constant value of 0 dB up until we hit S is equal to 1. And then we abruptly turn and have a slope of negative 20 decibels per dB beyond S is equal to 1. Now, we've seen frequency response plots before, and we know that they usually don't have sharp corners like this. So our approximation is rather good for S less than 1, and it's rather good for S greater than 1. But in the area of S equals to 1, that's where it gets a little bit wonky. So what we would really expect to see would be something more akin to this. Where at this frequency, S is equal to 1, we see that the value of our function is actually at 3 decibels lower than the 0 that our corner implies, right? This is our half power frequency that we talked about with regards to filters and all of that kind of good stuff in circuits too. So our hand-drawn Bode plot isn't going to take this into account because, again, it's nothing more than an approximation of what's going on before we hit our pole frequency and our approximation of what's going on after we hit our pole frequency. But realistically, we know that at exactly our pole frequency, we should have a value of negative 3 dB, negative 3.012 dB, I think if I'm remembering correctly, and we can smooth things out if we're so inclined to have a better grasp of exactly what's going on. But our hand plot seems pretty okay. All right, so we've talked about this simple pole. Before I move on to the next thing, does anybody have any questions about this? So negative 3 decibels literally represents the frequency at which our signal has lost half of its power, okay? So if we were looking at a voltage waveform specifically, if our voltage started at 1, this would be the frequency where it fell down to 1 over the square root of 2. Okay. So this is a constant value when we have a simple single pole like this. Whatever our pole frequency is for a simple pole, we should have a negative 3 dB drop in our response. Okay. So this is defining effectively. Actually, so let's take this one step further since you asked the question. What kind of frequency response or what kind of filter would have a response like this? A low pass, exactly right. So our low frequency signals are not in any way, shape, or form attenuated until we get beyond our pole frequency, at which point they start trailing off significantly, right? So high frequency signals are attenuated, low frequency signals are passed. So this is very much the response curve for a simple low pass filter with a pole frequency of 1 radian per second. And so that would have corner frequency of whatever 1 over 2 pi is. I think that's somewhere in the ballpark of 159 millihertz. we were so inclined. Okay. So let's mess with this very slightly. So what if we had a case where our transfer function was instead 1 over 1 plus s over 100? So how did I write this up here? So for s much less than 100, what does this look like? One over one again. And for s much greater than 100, what does this look like? Getting close to 1 over s again, right? So what's that going to do to our Bode plot? It's just going to shift this to the right to where our pole frequency is now at 100 radians per second. Graph is going to look exactly identical, except that it's slid over, right? So this basic fundamental building block of what's going on for a transfer function of 1 over s plus 1 translates to any first degree pole like this, except that we're just going to slide it around depending on what the value under the s is, right? So we had an implied s over 1 previously, giving us a pole frequency of 1. Now we have a pole frequency of negative 100 radians per second. So we simply slide that graph over to the right. So something akin to this. So let me make this longer. So if this was still 10 to the 1, it's going to be 10 to the 0, 10 to the minus 1, 10 to the minus 2, 10 to the plus 1, 10 to the plus 2, 10 to the 3, 10 to the 4. What we should expect to see is it's flat until we hit 10 to the 2, and then it rolls off at a slope of negative 20 dB per decade everywhere beyond that. And then our smoothed out graph would be something like that, right? So in general, based on just these two simple explanations, we have 0 decibels for s is less than our pole frequency, and we have a graph that is decreasing at negative 20 dB per decade for s greater than our pole frequency. If we were trying to construct a Bode plot or frequency response curve by hand, these are the rules, okay? So we're 0 decibels up until we hit our pole frequency, and then we are decreasing at a slope of negative 20 dB per decade for anywhere beyond our pole frequency. So how do you guys think our simple zeros are going to work? Pretty darn similarly, except that we're going to increase at 20 dB per decade. And let's see that just really quickly, right? So simple zeros. So let's say that we have h of s is equal to s plus 1. So for s less than 1, what is h of s approximately? 1, right? So something very small plus 1 is about 1. For s much greater than 1, we would have something very large plus 1 is approximately equal to that something very large.
So like, are you trying to say it's so big you just need like the one?
Yeah,
Okay.
that's it. That's all we're doing, is we're figuring out if we are far away from our exact zero frequency in this case. So if we're far to the left-hand side, what does it look like? Roughly 1. If we're far to the right-hand side, our curve should be almost exactly the frequency response of just s by itself. Okay. So putting these two things together, we would have h of s measured in decibels. 5, 6, 5. So 10 to the 0, they're in the middle, 10 to the minus 1, 10 to the minus 2, 10 to the plus 1, 10 to the plus 2. So something like this, where this is a slope of plus 20 dB per decade. And then my smoothed out response curve would be more akin to this, where once again, the difference between here and here, in this case, is going to be exactly positive 3 dB. So based on this frequency response curve, what kind of filter has a transfer function involving a simple zero? A high pass filter, effectively. So we start seeing that our system gain effectively starts increasing for frequencies beyond our full frequency. So effectively, high frequency signals in this case are amplified while lower frequency signals are left alone. This would realistically be more akin to an active high pass filter, just because we have a gain here, right? So this is no longer sitting at 0 dB, so we have to have some amplification in order to make our output signal larger than our input signal in that region. Okay. And then we can play around with this very slightly. What if we had h of s equal to 1 plus s over 100? What do you guys think is going to happen in this case? Slide the graph over to the right. And so our corner would be at s is equal to 100.
Theoretically, what were slopes like? What if just 100 over s? We go on the other side of the graph.
So if we had, let me write this out and then we'll talk about that. So put 10 to the 0 here, 10 to the 1, excuse me, 10 to the minus 1, 10 to the minus 2, 10 to the positive 1, 10 to the positive 2, 10 to the positive 3, 10 to the positive 4. Something like this. And then the smoothed graph would look something like that. All right, so just before I answer your question, Michael, let's talk about the general thing here. So in general, what we have is 0 dB for S is less than omega Z, and then we're increasing at 20 dB per decade for S is greater than omega Z. Now, this is an aside, so we don't need to write this down. I'm just trying to answer Michael's question. Okay. So you said, what if we have H of S was equal to 1 plus 100 over S? Okay, so let's think about this. So I might write this out as S plus 100 over S. Do you agree that that's the same thing?
Yes.
Okay. So it looks like I have a 0 at S is equal to negative 100 and a pole at S is equal to 0. And we know what both of those things look like. So let's write them down. You don't realize it, but this was literally my next topic anyway. So H of S in dB so here's S, right? So I'm going to do my numerator in red. And so that is having a 0 at S is equal to 100. Okay. So let me put my axes here. So 10 to the 0, 10 to the minus 1, 10 to the minus 2, 10 to the plus 1, 10 to the plus 2, 10 to the 3, 10 to the 4, and so on and so forth, right? So our 0 is going to give us a contribution of 0 up until 10 to the 2, and then we're going to increase at a slope of 20 decibels per decade. That line isn't as correct as I want it to be. Something like that, right? And then I'm going to do our denominator in blue, right? So that's just 1 over S effectively. So we would have something like this. And realistically, I'm going to keep this going. Okay. And let me do it one further. What I would do is literally just add these together point by point. So way back here at 10 to the minus 2, I have 0 dB plus what looks to me like 40 dB. Let me put some numbers on my y-axis so we can see where I'm coming up with these things here, right? So let's make this 0 dB plus 20 plus 40 minus 20 minus 40 and so on and so forth. Okay. So I have 40 dB plus 0 dB looks like 40 dB. So I'm just going to put a purple dot right here, and I'll connect the dots in a moment. Now let's look at 10 to the minus 1. So I have 20 dB plus 0 dB looks like 20 dB. Now let's go at 10 to the 0. 0 plus 0 is equal to 0. now I have 0 plus -20, which looks like -20. And right here, I have 0 plus -40, looks like -40. Now things are about to get interesting, right? So right here at 10 to the 3, I have positive 20 dB and I have negative 60 dB. So this is going to look like negative 40 dB again. And effectively what we're going to see is that this positive 20 dB per decade slope here cancels out this negative 20 dB per decade slope here. So everywhere beyond this point is just going to be flat. So when I have those two things put together, it should have a frequency response of something like this. So if I know how to deal with a simple pole, and I know how to deal with a simple zero, I can reconstruct the frequency response diagram for literally any transfer function that is composed of simple poles and simple zeros in any possible combination I could ever think of. Because it's literally just adding those responses up point by point. Yes. So there definitely would be a little smoothed out part right here for sure. But I'm not particularly worried about that because I'm doing a hand plot kind of thing, right? But you're 100% correct that we're never going to have a hard angle like this. It would be a smooth transition. Toby.
It's only works for one of each.
No. Good. In fact, let's show. Okay. So let's say that I had h of s was equal to 10 times s plus 1 times 1 plus s over 100 divided by 1 plus s over 0.1 times 1 plus s over 1,000. So this is multiple simple poles, multiple simple zeros, but we can employ the exact same approach. Okay. So I'm gonna give myself plenty of room here. This might be too much, but it'll be okay. Okay. So let's put 10 to the 0 right here. So this would be 10 to the -1, 10 to the -2, 10 to the -3, 10 to the +1, 10 to the +2. Nope, I've got something going on at 1,000, so I need to give myself a little bit more room. 10 to the 0, 10 to the -1, 10 to the -2, 10 to the +1, +2, +3, over here would be +4, okay? And then once again, every one of these tick marks on the vertical axis represents a change of 20 dB, okay? So let's start with just the 10 by itself. So let's do that in red. So what is 20 log of 10? Wake back up, there we go. So 20 log of 10 is 20. Okay. So we would have a constant line at 20 dB from our constant term out front. Okay. Now let's do this guy right here in blue. Okay. So that is a simple 0 at s is equal to 1, which means I'm going to have a flat line here up until I hit s is equal to 1 or 10 to the 0. And then I'm going to increase at 20 dB per decade. Like so. Now in this green, let's take care of this other simple point, right? Or excuse me, simple zero. So this is going to look like the exact same curve, except that it shifted over and it's going to start increasing at 10 to the 2. Now let's do this 0 in orange. So that's going to look like a flat line at 0 dB until we hit 10 to the minus 1, and then it's going to go down at a slope of negative 20 dB per decade. And then we have a pole at 1,000 or 10 to the 3. So let's do that one in purple. So constant all the way until here, and then like that. And then we would go through and we would simply add these up point by point, right? So at 10 to the minus 2, I have 0 4 times plus 20 dB. So there's my point for that guy. At 10 to the minus 1, I have 0 4 times plus 20 dB. We can see now that I'm going to have 0 3 times plus 20 dB minus 20 dB is going to look like 0. Then we have our zeros, 20 dB, 20 dB, and minus 40 dB. So that's all going to cancel out. It's going to stay 0. Um, 20 dB plus 40 dB is 60, minus 60, so those cancel each other out. $20 plus 20 plus 60 is 100, minus 80 is positive 20. And then effectively, we know that the slope of this guy is canceling this guy, the slope of this guy is canceling this guy, and so it's going to stay flat at just this 20 dB. We're going to get the same result by just adding them all point by point. So let me do it in a thicker thing. So this seems to be the frequency response curve of some sort of band stop filter. You have a pass band over here, attenuation, and then a pass band over here.
Oh, I meant, the second.
What do you mean the second?
Go down a little. Yeah. Thank you.
Oh, the transfer function is
Yeah.
what you wanted. Yeah, okay. So how did you guys feel about all of this? Not too bad. Okay. So everything that we've done to this point is dealing with amplitude. Now let's talk about our phase response as well, because we can use the information that we've done here to kind of figure out what's going on with that too. Okay. So for that in particular, though, we kind of can't use S anymore. Okay. We need to be looking at the explicit case where S is equal to J omega. So let's say Yes. Nah, you're good. No. So let's say that we have a simple pole. Okay. So if H of S is 1 over S plus 1, then H of J omega would be 1 over 1 plus J omega, right? So all I've done here is simply substitute in J omega everywhere I saw S. Nothing more complicated than that. Okay. So I don't like this because hopefully we can all recall that our phase response from circuits 2 was the inverse tangent of the imaginary part over the real part. That is what phase angle is by definition in polar form for complex numbers. That's that from circuits 1. So I don't have an easily defined real part or an easily defined imaginary part right here. So I'm going to have to multiply this guy by the complex conjugate of the denominator over the complex conjugate of the denominator to split this thing up. Okay. So if I multiply this by 1 minus J omega over 1 minus J omega, what I wind up getting is 1 minus J omega over 1 plus omega squared, or 1 over 1 plus omega squared minus J omega over 1 plus omega squared. Okay. So my phase response, theta, as a function of S, is the arctangent of the imaginary part. So that's going to be negative omega over 1 plus omega squared divided by the real part, which is 1 over 1 plus omega squared. And we should see that these two denominators cancel each other out. So we simply have the arctangent of negative omega. So if I were to make a plot, so this is our phase angle as a function of omega. And let's put 10 to the 0 right here, 10 to the minus 1, 10 to the minus 2, 10 to the plus 1, 10 to the plus 2, and so on and so forth. Let's use our calculators for a moment. And actually, let me make a note here. So this is going to correspond to positive 45 degrees, and up here is going to correspond to positive 90. This is 0 degrees. This is minus 45 degrees. And this is minus 90. So just using my calculator here, inverse tangent of 10 to the minus 2.
It's on the side of this, that's actually supposed to be negative 45 degrees on the upper part.
Plus. So I got 0.5729 yada, yada, yada degrees. So effectively, we're at roughly 0 degrees right here. It's not quite 0, but it's something pretty damn close. The inverse tangent of 1 over 10 is 5.71 degrees. So about right here. The inverse tangent of 1, yes. Well, I got 5.7, but I'm putting in a positive value and I should have been putting in a negative value, right? Because we're doing the inverse tangent of negative omega. So at S is equal to, or omega is equal to 1, we hit exactly negative 45 degrees. Inverse tangent of 10 is 84. So that's going to be about right here. Inverse tangent of 100 is 89 and some change. So it's damn near negative 90. And as we keep going on and on and on, it's just going to get closer and closer to 90 degrees. Okay. So for our smooth line graph, we would have something like this. What we're going to see is it's going to be at 0 degrees until we get to roughly a decade before our pole frequency, and then it's going to start to transition. It's going to pass through negative 45 degrees at exactly our pole frequency. And then it's going to come out and start turning about a decade after our pole frequency. And then it'll settle to minus 90 degrees. Our straight line approximation is effectively just, it's 0 until we hit a decade before, straight line through 45, hits negative 90, and it's going to stay negative 90 for all frequencies after, right? So effectively, we should see our transition our transition from 0 to 90 starts a decade before, and it ends a decade after our pole frequency. That's our general case, right? So in general, we have 0 degrees for omega is less than 0.1 omega z. And we have negative 90 degrees for omega greater than 10 omega z. And then we just connect the dots in the middle. And I'll put it actually as negative 45 degrees for omega is equal to omega z. And we just smooth that out. So this is what's going to happen to our phase response for every pole that we have, right? We're going to see that it has a value of exactly negative 45 degrees at our pole frequency, and then we've got this transition period, okay? If we had multiple poles, this will just happen multiple times. So for instance, if we had a transfer function where we had 1 over s plus 1 times 1 over s plus 1,000, we'd see this start to transition to another one, and we'd hit negative 135 degrees at s is equal to 1,000. Toby. We do. This 0 degrees right here. Oh, I'm sorry. All of these should be p's. That's just me not paying enough attention. Thank you for that. All of these should be omega p's. Thank you, Toby. Thank you. Okay. All right, so let's look at the phase response for 0 now. What do you guys think is going to happen? It's literally this exact same graph, except flipped about horizontal axis. Right. So if we had h of omega is equal to, excuse me, h of s is equal to 1 plus s, then h of j omega is literally just 1 plus j omega. And from that, we would have the arc tangent of omega over 1, which is literally just that graph flipped upside down. Ah, shit, omega. So something like that would be our smoothed response. Something like that would be our straight line approximation. All right, so if we were so inclined, we could figure out what the phase response of this guy would be as well. Right? So let's do that off to the right. So here was our magnitude response. So over here, let's do a phase response. Okay. So let's make this plus 180, 135, 90, 45, 0, minus 45, minus 90, minus 135, and so on and so forth. Yep. Not really. There. That was just me arbitrarily starting at 180. And it looks like based on what I have written down, we're not even really going to need it. But effectively, so let's see. So the phase response of the 10 by itself is going to be 0 degrees the entire time, right? 10 is never going to just magically turn into not 10 or J10 or negative J10. It's just 10. Yeah. So this guy out here contributes literally nothing. Okay. So then we have, so let's see. So we should have 45 degrees at 1. So let's define some things here. So let's make that 10 to the 0, 10 to the minus 1, 10 to the minus 2, 10 to the plus 1, 10 to the plus 2, 10 to the plus 3, and then we're so on and so forth, right? So actually, let's go through here more systematically, right? So at 1/10, we should be at -45. At 1, we should be at +45. At, actually, hold on. Sorry, I'm getting ahead of myself here. Okay, so let me explain this. We could draw all of them out and add them point by point and all of that kind of stuff like we've been doing. There is nothing wrong with that, but we can infer things pretty easily here as well. So this is our lowest thing that we're dealing with, right? This is our lowest frequency term, okay? So I know that if I'm starting at 0, which I have no reason to not start at 0, at 1/10, I should hit -45 degrees. This guy is going to change my phase by +45 degrees when I'm at 1. So we should be -45 plus 45, we should be at 0 right here, effectively. Okay. At 10 to the 1, which is after our transition happens, we're going to be at our full +45, right? So this guy is going to contribute an overall 90-degree phase shift, but it takes us time to get there. Okay. Now at S is equal to 100, which should be right here. We should be at, let's see, that's going to make it 45 more positive, so 90. Making this harder for myself. Also, I can't read my. You know what? I think this actually is just going to be easier just to do it point by point because I'm confusing the shit out of myself now. So let's just do it that way. Sorry for the confusion. Okay, so let's see. So S plus 1, we should have this. And this and this. 100. Point 1. And then didn't underline that one, but it looks like I was doing that one in purple. Yeah. So at 10 to the 3, I should be here. And let's just add all these things together. And I did that in this color. Okay. Yes. It should hit 45 degrees at 100. It's like this one hits 45 degrees at 10 to the -1, or -45 degrees at 10 to the -1. This one hits -45 degrees at 10 to the -3. This one hits +45 degrees at 100. This one hits +45 degrees at 1. Yeah. So remember, sorry, let me scroll back down here. In general, we're 0 until we hit 1 decade below our pole frequency. We're 90 as soon as we hit 1 decade after our pole frequency. We are at 45 at exactly our pole frequency. Okay. And so now when we add things together, point by point, all of these zeros add together to make 0. So we're just going to come down, go to here. Okay. Now I have positive 45 degrees and minus 90 degrees. So that's going to look like negative 45 degrees. So I'm just going to put that point there and connect these dots. Then up here, I'm at positive 90 degrees, 0, 0, negative 90 degrees. So those all cancel each other out. So I should be at 0 here. Now I have a 90 plus a 45, so that's 135, plus 0, so that's still 135, minus 90 is positive 45 degrees. And then here at 10 to the 3, I have 90 plus 90 minus 90, so that's 90 minus 45 is positive 45 degrees. And then I ran out of space, but effectively beyond this point, we would have had negative 90, negative 90, positive 90, positive 90. So we would have come back down to 0 at 10 to the 4. Toby. Not at all. The constant is a constant 0 degrees. Its phase does not change. Okay, so I apologize that I got myself a little mixed up there trying to draw the phase response graph in a fancy way when adding them together point by point works. It's pretty straightforward, so sorry for trying to get fancy on you guys and then reverting back to the method that works. So what we've dealt with today is Bode responses, both magnitude plots and phase plots for literally any combination of simple poles, simple zeros, poles at the origin, zeros at the origin, right? So we can have repeated real poles, all that kind of good stuff, repeated zeros, everything is encapsulated here. What we're going to talk about on Wednesday is how having complex conjugate poles or zeros messes this up. And that is going to lead us into our discussion on resonant circuits.